How did the non-living chemicals on Earth spark to life? In an earlier video, I explained why silicon-based life is next to impossible. Carbon, however, forms sturdy bonds with itself and other elements, but not so very strong that no other molecules can be spliced into the mix. Water is the medium that allows carbon-based molecules to be dissolved and metabolic reactions to take place. Ironically, the best solvent for a silicon-based metabolism is the carbon-based methanol. Anyway, the first organic molecules to begin forming on Earth were the nucleobases, relatively simple combinations of carbon, hydrogen, nitrogen, and oxygen. One such nucleobase is cytosine. The other four are adenine, guanine, thymine, and uracil. Just by examining their atomic structures, it's easy to see that it would be difficult to prevent their elements from bonding to one another. Electron shells seek to be filled, and for these four elements, the bonding comes naturally. The real effort would be to stop them from bonding. It is fair to say that the formulas for these 5 nucleobases would repeat without any pre-programming because they create the optimal fit. When these molecules begin to form is really not hard to surmise. We know that living genetic material breaks down at approximately the boiling point of water, and maybe a couple of degrees less. Keep in mind that we're not talking about evolved extremophiles. Liquid water, below boiling, seems to have first appeared on Earth about 4.41 billion years ago. So it's safe to assume that nucleobases began forming almost immediately hence. Directly following these molecules, simple sugar molecules possessing 5 carbon atoms were also able to form, as well as phosphorus-based molecules. These molecules are called deoxyribonucleic acids and ribonucleic acids. RNA has one more hydroxyl than DNA, and DNA has one more hydrogen than RNA. When these 3 types of molecules bound together in varying combinations, the new larger molecules became known as nucleotides. Even at this level of molecular complexity, it is debatable as to whether or not pre-programmed replication existed or was necessary. The atoms simply sought the best bonding arrangements. The next step in molecular construction, however, was a great evolutionary leap. Somehow, 3 particular nucleotides joined together to form a codon. Then, 3 different nucleotides formed another codon. The first codons were probably formed randomly according to the best fit rule, but soon after that, a system of replication must have developed. To this day, the same combinations of nucleotides form the same codons. Technically, one codon makes one amino acid, but there are 64 codons and only 20 amino acids that humans need. And combinations of 3 codons form amino acids. This is fine-tuning at the atomic level. But what is the intelligence that directs replication? For all intents and purposes, it seems that there's a singular, perfect fit or an equilibrium that all matter and energy in the universe seek out. For example, only a specific number of electrons are allowed per shell. Only 3 quarks can form a proton. Helium has no fit. For atoms, it seems that they poke around to find the sturdiest bonds possible. Sometimes the bonds are weak and sometimes too strong, but they are the best bonds available. My thinking is that atoms can detect the strongest electrical attraction, analogous to Geiger counters, and seek a bond with that particular source. Truly the forerunner of self-awareness. Mistakes destabilize bonds, and weak electron associations are pushed aside by the seeker with the strongest electrical attraction. This, I believe, is the basis of genetic transcription. The improvements in efficiency, even with all life's complexities, can be attributed to 4 billion years of repetition. With that said, amino acids surely abounded in the primordial oceans of the Hadean Eon. Proteins, the building blocks of living organisms, soon followed, along with specialized proteins called enzymes, which induce chemical reactions. Enzymes would eventually initiate the production of fatty acids and carbohydrates. Now the question of the ages is, when did life on Earth begin? For something to be considered alive, biologists have generally decided that 5 requirements must be met. 1. The potential organism must grow. 2. The potential organism must reproduce. 3. The potential organism must eat or consume energy. 4. The potential organism must shed waste in some form. And 5. The potential organism must respond to external stimuli. Biologists and affiliated scientists can surely add to and augment these necessary conditions, but the point is made that all living organisms must have a minimum threshold to cross. Now we come to the juicy discussions of what sparked these molecules to life. Religions speak volumes, yet so do atheists and men of science. It is still the same mystery now as when it was asked 1,000 years ago or even 10,000 years ago. So far, no one seems to be getting any closer to an answer. Or are we? Could it be that the cause of the consciousness of organisms on Earth is the same cause of molecular replication, which is the same cause of atomic bonding? Yes, it is the electron bond. A bond is formed when the electrons of 2 or more atoms share unfilled orbitals, and a bond can stay strong only if it is receiving adequate energy. The energy is delivered by photons. Molecules conserve energy remarkably well, but eventually even the bonds of electrons weaken and break down. To maintain the bonds, molecules have the ability to extract the photons of other molecules, thus consuming nutrition to survive. Even the food we eat today is ultimately converted into photons. ATP production is an example. In an environment where energy absorption is possible, those molecules on the receiving end can grow ever larger because the multiplying electron bonds are getting an adequate supply of energy. Consuming energy and growing. 2 requirements to be considered alive. 4 billion years ago, when molecules reached a maximum safe size limit, at the destabilizing threshold, the rudimentary beginnings of reproduction began. Just as viruses are simply broken off pieces of DNA called plasmids, pieces of molecules broke away from the parent to begin their own growth processes. Eventually, reproduction would become more developed, but the same break-off principle applies to the present day. Waste production is merely a byproduct of molecular reactions, energy-depleted molecule husks. Reproduction and shedding. 2 other requirements of life. Let's cut through all the talk and plainly state when life began. Life began when the first electron of either a hydrogen, an oxygen, or a nitrogen atom sought out a bond with a carbon atom. It was stimulated to do so, thus the first example of reacting to an external stimulus, the final requirement for life. In other words, consciousness, self-awareness, at its lowest common denominator, is seeking an electron bond with carbon. Once that first step was taken, the subsequent developments were a matter of complexity over time. We can really fine-tune this claim by adding that opposing electric charges constructed this first electron bond between one atom and carbon. At the risk of opening a can of worms, the 2 up quarks inside protons have positive charges, and together with the negative down quark gives protons a net charge of 1. Electrons have negative charges of 1. Sometime in the future, I think, physicists will realize that all fundamental particles are constructions of photons, uncharged particles. Assuming this is the case, then whatever charge is transceived at the quark electron level and not below. The bottom line is, The electric charge created life, and we are a long way from knowing what charge is. The next step would be that molecules would avoid environments that threaten to destroy their electron bonds, such as the dehydrating effects of direct sunlight or too much hydration. A recent discovery of a crystal of zircon suggests that life was already fermenting organic byproducts as far back as 4.28 billion years ago. This is difficult to verify, and there could be other explanations for this finding, but it's not far-fetched and it stands to reason. With such a broad definition of life, it is safe to say that the galaxy is teeming with it. But at what level of complexity is another story. That would depend on the limitations of the environment. In any case, we are not alone, not even in our own solar system. Thanks for watching. Talk to you soon.